Welcome back, mathematicians. In this video, we are going to graph a piecewise-defined function. A piecewise function is defined using different equations for different parts of the domain. So we really need to separate this out into three different graphs. I'm going to color code as I work through this problem. So the first graph, which is defined for the domain as x is less than -2, will be the equation y is equal to x plus 5. Now, because of the fact that that's a linear function, I know that it will be a line or some version of a line. Now, the domain, again, is x is less than -2 for this piece. Now, what I like to do is make an xy table using the domain to pick the correct x coordinates that I'm allowed to use for this piece. I'm allowed to use values that are less than -2. So I'm going to pick -3 and -4. But I'm also going to pick -2. And the reason I'm picking -2, even though it says x is less than -2 and not equal to -2, is because there's infinite points, infinite values between -2 and 3 that need to be included on my graph that still satisfy that inequality. So think of -2 as a boundary. And because it's a boundary, but not necessarily part of my domain, I'm going to use an open dot for that point. Now I'm going to insert or evaluate this equation for the values of -2, -3, and -4. So -2 plus 5 is +3, -3 plus 5 is +2, and -4 plus 5 is +1. So let's go to my coordinate plane and let's plot these 3 points. So to the left 2 up 3 units, I'm going to put a point, but again, it's important to note that that will be an open point. So I'm going to make it large and exaggerated there. -3 comma +2, that'll be a solid point, and -4 comma +1. Now again, we can keep going. In fact, using the slope, we can find even more points. And so it's important to note that this will be a ray that never stops, which is why we must include an arrow at the end of that ray going down and to the left. And so that is the first piece of my piecewise defined function. Now to my second piece, which is y equals negative absolute value of x plus 3. So again, I'm going to make a table, and I know that I have to satisfy the domain of -2 to +4, including -2, but not including +4. So I'm going to start with -2, and this will be included in my domain. I'm going to pick a couple other values, so how about -1, 0, 1, and then I'll stop at +4. And yes, +4 again will be included even though x is not equal to +4 because I need a boundary there. And in that boundary, or on that boundary, I'll put an open dot one more time. Now I evaluate my function for all of these 5 x coordinates. I'm going to input them into x, take the absolute value, apply the negative, and add 3. Now, let's do this one a little bit slower, making our table a little larger. So what I'm going to do here is write out y is equal to negative absolute value of x plus 3 in the second column, and then in the third column, I will evaluate. Absolute value of -2 is +2, but then we make it negative again, and it becomes -2 plus 3, which is +1. So that's my y coordinate. Now for -1, I have negative absolute value of -1 plus 3. So the absolute value of -1 is 1. Apply the negative, you get -1 again, and then plus 3, you have an output of 2. Apply the input of 0. Absolute value of 0 is 0. There is no -0, so we still just have 0. Plus 3 is 3. Now we will take the absolute value of 1, which is 1. Apply the negative, we get -1. Add 3, we get +2. Last one, we apply the absolute value of 4, which is 4. Now the negative, which is -4, and then add 3, we get an output of -1. Now let's go ahead and plot these 5 coordinates. So -2, or to the left 2, up 1, put a solid point. -1 up 2, 0, 3, 1, comma 2, and then 4, comma -1. But at 4, comma -1, one more time, will be an open point. What we know is that the absolute value does create a V-shaped graph, and so in this case, it's part of that V-shaped graph with no arrows because we have a beginning to our domain and then a boundary for the end of our domain, which is at positive 4. Let's now go to the last piece, which again is another linear function, y equals 2x minus 3. Let's create our xy table, and this says x is greater than or equal to 4, which means I'm going to pick 4 and values larger than 4. So I'll pick 3 values, and so we will evaluate the function at a value of 4, 5, and 6. Or we could evaluate the function at 4 and then use our slope to get more values if we choose to do that. 4 times 2 is 8, 8 minus 3 is 5. 5 times 2 is 10, 10 minus 3 is 7. And then 6 times 2 is 12, 12 minus 3 is 9. So we have to the right 4, and all of these dots are going to be closed dots, including the boundary of 4, 5. So at 4, 5, put a solid or closed dot. 5, 7, put another solid dot, and 6, 9. Now because we could continue going up and to the right to infinity, we do draw our ray, and we keep drawing with an arrow at the end to the right. And so this is the graph of our piecewise function. Now a couple quick notes about our piecewise function. Let's identify the domain. Now it looks like the domain is broken because we have these gaps, but in reality it's not. So it's undefined at an input of -2 here with this piece, but then it is defined at -2 with this piece. So therefore it is defined at -2 and there is no gap. Same is true also for 4, which means the domain is going to be the set of all real numbers, or -infinity to infinity. Now the range is interesting because there is a gap. And so the range is defined from -infinity up to the highest point for these two curves, or these two pieces of the graph, which happen to be positive 3. Now since it's defined for positive 3 with the absolute value part of the function, we will put a bracket. Then there's a gap, and the function picks back up at positive 5 for my y coordinates, so we start at positive 5, including positive 5, and we go to infinity. All right, guys, good luck.